Hello everyone and welcome to a new video. Today I'd like to talk about how we can measure glucose in the urine. How we can measure the level of glucose in the urine. This is important as high glucose in the urine indicates hyperglycemia or high glucose levels and potentially diabetes. So normally our kidneys actually reabsorb all the glucose back to the blood. But if we have so much glucose in the blood, the kidneys can't keep up and some will end up in the urine. So before we discuss how we measure glucose in the urine, let's first review the basic structure of glucose. So as you can see here, glucose is actually a 6-carbon molecule, and it's a monosaccharide with the formula C6H12O6. Okay, and it can exist in either a linear form, okay, as an aldehyde, and we call it an aldose or an aldohexose because it's an aldehyde with 6 carbons. I didn't really draw it here, but it can exist either in a linear form as a 6-carbon aldehyde, we call it an aldohexose, or it can exist as in the ring form, as a ring, specifically as a 5-carbon ring known as a pyranose. And I drew it here, numbering the carbons in blue, 1, 2, 3, 4, and 5. So 6 carbons in total, but 5 carbons in the ring. That's why we call it a pyranose, right? 5-carbon ring, but 6-carbon molecule. In contrast, if we look at something like fructose, fructose is a furanose, which means that it has 4 carbons in its ring, but glucose has 5 carbons, so that's why it has a pyranose ring. I put it right here. Now, in sugars, this CH2OH group that I drew here, right? So this is the 6-carbon, carbon number 6. This group can either point up or down. But naturally in our bodies, it's pointing up. And this is known as the D form. So I put here D-glucose and I put an arrow indicating this points upwards. The L form points downwards. But the L form is not natural. It's not found in the biochemistry of life. So glucose in our body naturally is found in the D form, which means that CH2OH group right here is pointing upwards. Also, the first carbon here, this carbon right here, the first carbon of the ring, number 1, is known as the anomeric carbon, So this carbon right here is known as the anomeric carbon. And the OH that's attached to this anomeric carbon can again either point up or point down. If it would have been pointing down, it would have been alpha. In alpha, the OH points down. So glucose is a B-D-glucose. The B refers to the OH of the anomeric carbon pointing upwards, and this CH2OH group pointing upwards, right? And this is the 6th carbon. Okay? And the easy way to remember that this is beta because it points up and not alpha is because beta and balloon starts with the same letter and balloons float upwards. So in glucose we have this beta form and the D form, which is found naturally in the biochemistry of life. So that's glucose. It's a beta D glucose. And the interesting thing about this molecule, and this is really interesting, is that if nothing attaches to this anomeric carbon, or any monosaccharide, disaccharide, polysaccharide, if nothing is attached to this anomeric carbon, that means it can open up to the straight form. So it can go from the ring form back, in the case of glucose, to its aldohexose form, to its linear aldehyde form. Right? So, and also in this form, not only it can open up, it can also act as a reducing sugar, meaning it can actually reduce another molecule by adding H's to it and electrons. So it can actually reduce a solution that we call copper-Benedict solution. This is really, really important. So this reducing sugar, because nothing is attached to the anomeric carbon, can actually reduce a solution containing copper, known as the copper-Benedict solution, by adding H's and electrons to it. Specifically what happens, I drew the reaction right here. The copper 2+ in the Benedict solution is going to be reduced by the reducing sugar to become copper. So this is a reduction reaction. So the copper-Benedict solution is acting as the oxidizing agent, but it gets reduced. This reducing sugar is actually being oxidized, and it's acting as a reducing agent. It helps reduce the copper-Benedict solution. And as this reduction takes place from copper 2+ to copper, there's going to be a color change in the Benedict solution, going from blue to green to yellow to orange to red. So what's going to happen is, as the amount of reducing sugar in the urine goes up, it's going to change color. So if it stays blue, it indicates there's no reducing sugar in the urine. But if it turns red all the way, it means there's a lot of glucose swimming in the urine. So you can determine the amount of glucose in the urine by looking at the color change. The more it goes from blue to red, the more reducing sugar, glucose in this case, reducing sugar, glucose, present in the urine. And the higher, therefore, the risk for diabetes, as the kidney's transporters are saturated. So not all the glucose is reabsorbed. So some of it end up in the urine, I'm sorry. So because not all the glucose gets reabsorbed, because the transporters get saturated, some ends up in the urine, causing a color change in the Benedict solution, causing it to turn red. And that indicates the presence of reducing sugar in the urine.